Hello everyone, this is the solution video to AMC12 practice part 2 complex numbers. Let's do question 1. For how many integer n is n plus I to the fourth power a integer? So let's do the binomial expansion for n plus I to the fourth power. N plus I fourth power, this equals n choose 0, 4 choose 0, and 4 choose 1, and cube I, 4 choose 2, and square I square, 4 choose 3, and I cube, 4 choose 4, and 0 I fourth. So when we expand it, we have this equals n fourth plus 4 n cube I, 6 n square I square, 4 n I cube, and plus I fourth. Since we know I square equals minus 1, so I fourth equals 1. This equals n fourth plus 4n cube I minus 6n square minus 4n I and plus 1. So let's separate the real part and the imaginary part. It equals n fourth minus 6n square plus 1. That's the real part. As for the imaginary part, it is 4n cube minus n times I. It is an integer. That means we must have 4n cube minus n equals 0. There's no imaginary part. In order to make this to be 0, we see that we have n cube minus n equals n times n plus 1 and minus 1. It should be 0. And then we see the value of n should be 0, minus 1, 1. Therefore, there are 3 values for n to make this expression an integer. The answer here is 3. Question 2. M and n are 2 positive integers such that root 3 plus I to the m's power equals 1 plus I to the n's power. What's the least possible value of m times n? So here, the key is to use Euler's formula. Let's recall Euler's formula. It says that exponential I theta, this corresponds to cosine theta plus I sine theta. So here, we try to write above complex numbers in terms of exponential function. Notice that root 3 plus I, we can factor the modulus 2 times root 3 over 2 plus 1 over 2 I. And this corresponds to twice cosine pi over 6 plus I sine pi over 6. And accordingly, this equals twice exponential pi over 6i. Now, let's do the other part, 1 plus I. The modulus here is root 2, so we factor root 2. This is root 2 over 2, the real part, root 2 over 2i, the imaginary part here. So this corresponds to root 2 cosine pi over 4 plus I sine pi over 4. So accordingly, this equals root 2 exponential pi over 4 I. Let's plug in this into the given equation. So we have 2 exponential pi over 6i to the m's power equals root 2 exponential pi over 4i to the n's power. Now let's just do the modulus part and the exponential part. This 2 to the power n exponential m pi over 6i equals root 2 of with power n, that's equivalent to 2 with power n over 2. Exponential n pi over 4i. Okay, two complex numbers are equal in the exponential form. We should have the following requirement. First, their modulus equal. So 2 to the n equals 2 to the n over 2. The exponential parts are the same, means they are pointing the same direction. In other words, the difference of these two angles, so n pi over 4 minus n pi over 6, this should be a multiple of 2 pi. That's called 2k pi. Right, so first we find a relation between m and n from the first equation. Let's call this first equation, this is second equation. The first equation says that because they have the same base 2, so the exponential part equal. So m equals n over 2. In other words, n equals 2m. So n is twice m. Now let's plug in this into the second part. We should have n over, okay, I'm going to replace n by m. So the first part becomes pi m pi over 2 minus, okay, m pi over 6. It is 2k pi. In other words, we have m over 2 minus m over 6 equals 2k. So that is m over 3 equals 2k. In other words, m equals 6k. Remember, in this problem, we're looking for the minimum possible value of m times n. So we should make m as small as possible. And they are all positive integers. So m, the minimum value of m is basically 6. It's a multiple of 6 and it's positive, so it's 6. And then we have the minimum value of n. It's always twice of m, so it is 12. So m times n equals 72. The smallest possible product here equals 72. Question 3. Z and W are two complex numbers, such that Z has the modulus 2, W 3, and the difference has modulus 4. What is the modulus for the sum? Right here, let's use the definition of this modulus and its property. So we notice that Z modulus equals 2. Basically, we see Z times Z bar, the conjugate, actually equals Z modulus square. So that means this is equal to 4. Also, W here equals 3. We get W times W bar, the conjugate, equals W square equals 9. All right, next, let's apply this to Z minus W. Z minus W is 4. So we see that Z minus W times its conjugate. Z conjugate minus W conjugate. It's basically Z minus W square. And this is equal to 16. On the other hand, let's open this multiplication here. It is Z times Z bar minus Z times W bar minus Z bar times W and plus W times W bar. And we see this equals Z square plus W square and then minus Z times W bar plus Z bar times W, right? So we know Z and the W, so we can solve the parentheses part. Z times W bar plus Z bar times W. This equals 4 plus 9 minus 16, okay? Because this part equals 16 and this equals 4, this equals 9. So this equals minus 3. Next, let's apply that idea to z plus w. So we have z plus w and times z bar plus w bar. So we know this equals z plus w, the modulus square. When you open it, we have z times z bar plus z times w bar plus z bar w and plus w bar. Right, so we have this equals z square plus w square plus z w bar z bar w. And this equals 4 plus 9 plus minus 3. So we know this equals 10. And we also know that this equals z plus w square. So combining this, we see that z plus w has the modulus equals root 10. So the answer here is root 10. All right, for question 3, let me also provide you another method based on geometric interpretation. So let me call this method 2, using geometry. We know complex numbers are closely related to geometry. Let's draw this complex plane. This is the real part, and this is the imaginary part. So z has the modulus 2. So we can basically draw the length 2 here. So somewhere, this is z, okay? I'm using a vector. Now w has modulus 3. So I'm going to draw 3 here. That's w. Right, here we have z minus w has modulus 4. Okay, that basically means the distance between z and w equals 4. So let me connect this. So this is the z minus w. This vector or this complex number has length 4. Okay, we're looking for z plus w. So this is related to the parallelogram expanded by z and w. So let me draw a parallelogram. So this one is also w. It's parallel to w. I just shifted. And this one is equal to z, right? So what is z plus w? Z plus w equals the diagonal from O to this new point. This is z plus w, right? So here we recall a property on parallelogram. If we have a parallelogram, let's call it ABCD, we have the following property. If I connect AC and BD, we have AB square plus BC square plus CD square plus DA square. That's basically the sum of squares for every side. And this equals the sum of diagonal squares. So AC square plus BD square. Okay, this can be proved by using Pythagorean theorem. Well, you can draw a height from each side, and I'm not going to prove it here, but this is probably is useful in solving question here. So basically we have, if you apply this property to this problem, we have z square plus w square and plus z square again plus w square again. This is sum of squares of 4 sides. It equals z minus w, the modulus square, z plus w, the modulus square. And then we can plug in the numbers. Z square equals 4, 9, 4, 9, equals 16 plus z plus w squared. And very quickly, you can solve z plus w. This equals root 10. So we get answer equals root 10. Question 4. Here we have a set defined as z minus w. Z has modulus 2, w has modulus 1. Find the area of this set S. So let's find a way to describe this set. Because z has modulus 2, we can write z equals 2 exponential I alpha. Alpha is the theta, the angle here. So alpha could be any angle between 0 and 2 pi. So it goes through all such z. Similarly, w equals exponential I beta. Also, beta can be any angle. So let's see, it's between 0 and 2 pi. Next, we like to describe z minus w. Well, here I'm going to find its modulus, z minus w, because angle could be any direction, right? So basically, we consider the modulus. The shape should be symmetrical in any direction. The z minus w squared is basically z minus w times z bar minus w bar. So that corresponds to twice exponential I alpha minus exponential I beta times its conjugate, twice exponential minus I alpha minus exponential minus I beta. Now we expand this, we got 2 times 2, which is 4, 1 times minus 1 times 1 is 1, which is 1, and minus 2 exponential I alpha exponential minus I beta, and minus twice exponential minus I alpha exponential I beta. Right, so we can combine this to be 5 minus twice exponential I alpha minus beta, and plus exponential minus I alpha minus beta. Right, we can still recall the Euler's formula, okay? So it's going to be 5 minus twice. The first exponential equals cosine alpha minus beta plus I sine alpha minus beta. And the second one is cosine negative alpha plus beta. So it's also, let me write down, minus alpha beta. But that's equivalent to cosine alpha minus beta. And plus I sine negative alpha minus beta. Because sine is an odd function, so these two sines cancel each other. But these two cosine are equal. So finally, we have that this equals 5 minus 4 times cosine alpha minus beta. So this describes the modulus. And this shape is symmetrical in any direction because angle could be any. So here we see that z minus w squared is always larger equal to 5 minus 4. And last equal to 5 plus 4. The reason is because cosine function is between minus 1 and 1. That's why we have this. In other words, left hand side is equal to 1, on the right hand side is equals 9. So we see that z minus w, the modulus is between 1 and 3. And this picture is symmetrically in any direction. So that's basically the region between two circles. Two circles. Small circle is unit circle 1. Big circle is radius 2, 2. Because z minus w is between 1 and 2, so that covers the region between these two circles. Let's analyze. This is the set of S. So the area is pi. Okay, I made a mistake. Here should be 3. Should be 3. Pi times 3 square minus pi times 1 square. So it's basically 8 pi. The total area is 8 pi. Question 5. Zn is a sequence of complex numbers. And then we define Zn as following. And let m be the integer part of the following summation. What is the remainder when n is divided by 11? So here, each term is zk plus 1 minus zk squared. So let's try to simplify this expression. So zk minus 1, we know this equals 1 plus I. That's 1 plus I over root 2. 1 plus I over root k. 1 plus I over root k plus 1. Right? And also zk is 1 plus I. 1 plus I over root 2. Up to 1 plus I over root k. If we do subtraction, we will have the following. zk plus 1 minus zk equals 1 plus I times 1 plus I over root 2 all the way 1 plus I over root k times the difference of the last term. Okay, last term here I can add 1. So the difference of 1 plus I over root k plus 1 and 1, the difference equals I over root k plus 1 because the 1 cancels. And next, we shall consider its modulus because in the summation that's modulus square. And now notice that we have 1 plus I over root n. This is equivalent to root n plus I over root n. If we take the modulus, it's basically root n plus 1 over root n. Now let's apply this to zk plus 1 minus zk. Its modulus, the first term is basically root 2 over root 1. The second term is root 3 over root 2. And next term we know is root 4 over root 3. We see this pattern. Up to, this is root k plus 1 over root k. And the last part contribute 1 over root k plus 1. And now we can do some cancellation. This root 2 cancel root 2, root 3 cancel root 3, and we so this root 4 will be canceled. Finally, we cancel root k and also root k plus 1. So this corresponds to 1. In other words, if you square it, it's also 1. This also equals 1. Now we see the summation. Let me call this to be S. We see the summation S is going to be 2021. There are 2021 terms. Every term equals 1. And that's also the integer part. So that's also n. Now we just divide 2021 by 11. So we see 2021 divided by 11. It is 11 times 183 and plus remainder 8. So our remainder here equals 8. The answer to this problem is 78. Question 6. Let Z1, Z2 up to Z20 to be complex numbers associated to the vertices of regular 20 gun inscribed in the unit circle on the complex plane. Okay, now we take 1995th power for every such complex number. How many different values are possible? So here, let's try to express these vertices. because we have a regular 20s count inscribed on UD circle. Let's mark the first vertex here in the first quadrant. Maybe here. Let me call this A1. And also the next one will be A2. Maybe A3. All the way, okay. And maybe here, all the way up to A20. So we know the whole circle has 2 pi. That means the angle between any two vertices here should be 2 pi over 20. That's the angle. Right. Here I'm going to assume A1 corresponds to angle theta. By Euler's formula, we know A1 corresponds to Z1. It is cosine theta plus I sine theta. Okay. And next, we can express every other vertices in terms of Z1. We basically rotate every vertex by 2 pi over 20. So we have Z2 equals Z1 rotated counterclockwise. So it's 2 pi over 20 I, okay? And Z3 equals Z1 2 pi over 20 I, but times 2, rotated twice. And similarly, okay? So basically we can consider ZK equals Z1 exponential 2 pi over 20I rotated K minus 1 times. Right, let's write down the expression. So ZK is basically cosine theta plus I sine theta times the other part is basically cosine pi over 20 plus I sine pi over 20 and with power K minus 1. Right, next we are going to take 1995th power. So ZK 1995 equals cosine theta plus I sine theta 1995 times cosine pi over 20 plus I sine pi over 20 1995. Of course, don't forget this K minus 1. So remember, for if it's 20th power, that becomes 1, right? For this the second part. Let's see, 1995 when divided by 20, the remainder here equals 15. It's 20 times 99 plus 15. So I can basically replace this 195 by 15 because it's periodic by 20. So here, okay, by de Morphy's theorem, we have this to be 1995 theta plus I sine 1995 theta. That's the first part. We cannot simplify because we don't know theta. But for the second part, this corresponds to pi over 20 times 15, okay? Which is 3 pi. Okay. Okay, I think it should be 10 here. It should be 10 here. Because I divide by 2, so it should be 10 here. That's typo. So when I multiply 1995, it's equivalent to multiply 15. So this corresponds to 3 pi over 2 plus I sine 3 pi over 2. And with power K minus 1. All right, now we can simplify. The second parenthesis here basically equals minus I, because cosine 3 pi over 2, that's just 0. So this is basically cosine 1995 theta plus I sine 1995 theta times minus I k minus 1. And here k from 1 to up to 20. And we know I is periodic with respect to 4, right? So basically, the second part only has 4 different values. 4 different values. Maybe it is 1 minus I, minus 1, and I. Okay. There are 4 different values. So accordingly, the original expression has only 4 different values. Here, k applies to any number from 1 to 20. So the answer in this question is 4. Question 7. Z is a complex number satisfying the following equation. What's the sum of all possible values of z plus z conjugate over 2? So here, let's try to solve the value of z. From this equation, we can basically determine the imaginary part of z, because on the left-hand side is z plus twice modulus of z equals 13 plus 4i. And notice that the second term on the left, that's real number. That's real number. So if there's any imaginary part, it comes from z. On the right-hand side, we see the imaginary part equals 4i is 4, okay? So we can basically set z equals a plus 4i, because we are sure the imaginary part is 4. And here's a is a real number. It's a real number. Now let's use this and solve the value a. On the left-hand side, it is a plus 4i and plus twice the absolute value of z, which is twice square root a squared plus 16. This equals 13 plus 4i. We can cancel this 4i and derive the following part, which is a plus twice root a squared plus 16 equals 13. Let's separate the square root part and the part without square root. This is twice root a squared plus 16 equals 13 minus a. Then we can square both sides. The left-hand side becomes 4 times a squared plus 16. And the right-hand side is 13 minus a squared. Now let's open the squares. Left-hand side is 4a squared plus 64. The right-hand side is a squared minus 26a plus 169. We simplify this into 3a squared plus 26a minus 105. Okay, now let's come to see what's the expression z plus z conjugate over 2. This term is exactly a. You cancel the imaginary part. The question asks for all possible, the sum of all possible values of this expression, which is all possible value of a. So we have the 2 roots from this quadratic equation. The sum of the roots comes from the Vieta formula, which is minus 26 over 3. That's why our answer to this question is minus 26 over 3. Question 8. 2 complex numbers, z and w, satisfy that the modulus of z equals 4, and the equation holds. So modulus of z equals 4 implies z times z conjugate is the square of modulus of z equals 16. And let's also expand the second equation. It says that 14 plus 3i equals z plus w conjugate times z conjugate minus w. it equals z times z conjugate minus z times w plus z bar w bar minus w times w bar conjugate. And then this equals z modulo square minus w modulo square. And also plus minus zw plus z bar w bar. So here, let me claim the second parentheses are purely imaginary numbers because z, w, and z conjugate, w conjugate, they are conjugate to each other. So z conjugate w conjugate, this equals z w conjugate. So let z times w equals a plus bi. Then we have z w conjugate equals a minus bi. So in this way, we can find that minus zw plus z conjugate w conjugate, this equals minus a minus bi plus a minus bi. So we don't have a anymore. They cancel each other. Minus twice bi. So the second parenthesis equals corresponds to the imaginary part. And we see that this part equals 3i because the whole expression equals 14 plus 3i. And accordingly, the first parenthesis must be the real part, which is 14. From here, we can solve the modulus of w because we already know z conjugate square is z up modulus square is 16. So that implies w modulus square equals 2. Right, next we come to solve the second expression. Let's see, the second part here is z plus twice w conjugate times z conjugate minus twice w. Now let's open this. It equals z times z conjugate minus twice zw plus twice z conjugate w conjugate minus 4 w conjugate. And see, we have the real part is z square minus 4 w conjugate modulo square. And the second part is twice minus z w plus z conjugate w conjugate. So we are able to compute this value. The first part, z square is 16 minus 4 times w square, we already know that's 2. And the second part is twice of 3i because the second parenthesis is 3i. In this way, we solve this equals 8 plus 6i. And therefore, if we consider the modulus, it's basically 10. So this equals 8 squared plus 6 squared and square root here equals 10. Right? So that's why our answer to this problem is 10. Question 9. Here v is a given complex number. Z is complex number such that z minus v, z plus v, and the 0, the origin, form a right triangle. And the right angle is at origin. The area is given by root 3 over 2. What's the second largest possible value of z minus I modulus? So let's try to figure out this triangle. First, we notice that v is given. So let me draw z on the complex plane. Minus root 3 over 2, the real part. And the 1/2, that's the imaginary part. So basically, v is this complex number, this vector. And next, we see that one side of this right triangle is formed by z minus v and z plus v. Let me denote the point. z minus v by a and z plus v by b. And of course, the origin is the right angle vertex. Now we see the length of AB, which is the hypotenuse. Length of AB is basically equivalent to the modulus of 2v, a minus b, right? B minus a, 2v. And we know this is 2 because v has modulus 1. And now we see that suppose the height triangle AOB, this is the right triangle, and we have angle AOB, the right angle. Let me assume the height on AB, on the hypotenuse, let's h, okay? So the area is 1/2 times the AB, which is 2, times height, which equals √3/2. From here, we see the height is √3/2. Okay. Next, we can draw a circle with radius √3/2. And we should have the hypotenuse AB tangent to this circle. Let's draw a circle. For later discussion, let me draw a couple of circles here. Here, the circle has a radius √3/2. Still √3/2. All right, so let's see what's the shape of this right triangle. Because AB is perpendicular to the height h. This height is perpendicular to the hypotenuse AB. And we know AB, the direction is the direction of V. So the height direction is perpendicular to AB. So the height direction points to the following direction. Here is 60 degree, pointing to this direction. That's perpendicular to AB. I'm drawing 4 pictures because there are 4 cases I will discuss later. 6 degree, 6 degree. Okay, 60 degree. Now, the hypotenuse is AB is tangent to, is perpendicular to this direction. So there are following few cases. Because the right angle at O, so we can draw right triangle this way. The tangent point is here. In this way, we have the height is the radius of the circle, √3/2. In this way, we got point B on the y-axis, point A on the x-axis. That is the first case. And second case, we could shift this a little bit. We could have a here, this 30 degree, and pointing to here. Another 30 degree here. This is also possible. I just shift this by 30 degree. So according to the midpoint of AB corresponds to the Z, okay, corresponds to Z. So for example, in the first picture, here is the midpoint. That's the Z. Let's call it Z1. The second picture, here is the midpoint Z. Let me call it Z2. And it's also possible that AB is on the different quadrant. Let me show you this picture by symmetry. Perpendicular here. So this is A, this is B. So the midpoint is the corresponding z, okay, z. So let's call it z3, the midpoint of AB. And finally, I can also shift this here to get last case here. Every time we have right angle at the origin, okay? Right angle at origin. This is B and this is A. So this is midpoint is Z4. So in this way, we find 4 possible Z's. Now the question asks for the second largest possible value of Z minus I modulus. The second largest one. So Z minus I is the, actually this corresponds to a distance from Z to I. So I is here. Actually, this is I. This is I. And this is I. This is I. So we would see that Z4 is farthest from I. So Z4 minus I is the largest value. But second one is Z3 minus I. The third one would be Z1 minus I. And the last one closest to I is Z2. So Z2 minus I smallest one. So we can do some computation to show. First, let's see. Let me compute this solution here. Z3, that's the second largest distance to I. So Z3, we see that A has the coordinate minus I, and B has root minus root 3, 0. That's coordinate AB. So actually we have Z3. Z3 is minus root 3 over 2, the x coordinate, and y coordinate is minus half. And in this way, we can get Z3 minus I equals minus root 3 over 2 minus 3 over 2I. Its modulus equals root 3. This is root 3. So our answer to this question is root 3. Maybe we also need to double check Z4 is indeed the farthest point to I. So that's not hard. So we can basically find the coordinate B and A. And you will see actually Z4 equals minus root 3 over 8 minus 7 over 8I. So Z4 minus I is equal to minus root 3 over 8 minus 15 over 8I. So we see that Z4 minus I, at least this is larger than 15 over 8, but that's already larger than root 3. So we are sure the answer in this question is root 3, the second largest modulus, root 3. Question 10. Z1, Z2 up to Z2021 are distinct solutions to the following equation. Z2021's power equals 1. And what's the following summation? Let's first express these solutions. So by root unity, we see that zk can be expressed as exponential 2k pi over 2021 with I here. So that's in Euler's formula. This is equivalent to cosine 2k pi 2021 plus I sine 2k pi over 2021. And here k is 1, 2, 3 up to 2021. Okay. Next, let's try to rewrite the following summation. And we'd like to simplify 1 minus k, zk. 1 minus zk is 1 minus cosine 2k pi 2021 minus I sine 2k pi over 2021. Now let's apply double angle formula. Double angle formula says that cosine 2 theta equals 1 minus twice sine theta square, and sine 2 theta equals twice sine theta cosine theta. Those are double angle formula for cosine and the sine. Let's apply here. When I see the left and the first parenthesis equals twice sine square k pi over 2021. And the second one is minus twice I sine k pi over 2021 cosine k pi over 2021. Now we can factor twice sine k pi over 2021. This is going to be twice sine k pi over 2021 times sine k pi over 2021 minus I cosine k pi over 2021. Right, so we are able to simplify the modulus. Here, notice that the parentheses, this part will have modulus 1, which is implied definition. So sine k pi over 2021 minus I cosine k pi 2021. Well, this is basically sine k pi over 2021 square plus minus cosine k pi over 2021 square. Then we take square root. That gives 1. Okay, that gives 1. So if we take the modulus for 1 minus zk, we only have the first part, 1 minus zk, the conjugate, the modulus equals twice sine k pi over 2021, the modulus. Well, yeah, absolute value. So that's why here we have square in this question. So let's apply square. If we have square, we can remove the absolute value. It is basically 4 sine square k pi over 2021. Now let's again apply the double angle formula for sine. Okay, so basically the equation here. So we applied it. We see this equals twice 1 minus cosine 2k pi over 2021. Right, next, let's do summation. Okay, in the question, we just sum up these 2021 terms. So if we do summation, we have the following. Okay, from 1 to 2021, 1 minus zk square is equivalent to summation. Okay, from 1 to 2021, twice 1 minus cosine 2k pi 2021. So you will see this equals summation of 2, right? Okay, from 1 to 2021, sum of 2021 times minus twice, okay, from 1 to 2021, cosine 2k pi 2021. So the first part is easy to see. The first part, the sum equals 4042. And the second part, we like to claim this part equals 0. This part equal to 0. And while that's basically corresponds to the real part of the summation of zk, let's quickly show that. So okay, from 1 to 2021 cosine 2k pi 2021. This is basically the real part of zk. Or we can do this as the real part of the summation zk. Zk. And we know zk is basically case power z1. Okay, from 1 to 2021, this is z1 to the case power. And then we take summation. This summation is z1 times 1 minus z1 2021's power over 1 minus z1. And we know z1 is a solution of the z1 with 2020 first power equals 1. So this equals 0. And that's why the above summation of cosine equals 0. So finally, our answer is basically 4042. 4042 here. Question 11. Z and W are two complex numbers satisfying Z has modulus 1, W has modulus 2, and the following equation holds. So we need to find the distance between Z and W. So let's, by the modulus, let's write Z as exponential I alpha and W as twice exponential I beta. Now we need to use the equation to find some relation between alpha and beta. So W squared plus 2WZ plus 4Z squared equals, okay, this equals 0. On the other hand, W squared equals 4 exponential I times twice beta. And 2WZ also equals 4 exponential I alpha plus beta, okay, multiplied together. And then 4Z squared is 4 exponential I twice alpha. So this equals 0. That implies, I can just remove 4. That implies I exponential I 2 alpha plus exponential I and 2 beta plus exponential I alpha plus beta and equals 0. Actually, I can factor exponential alpha plus beta. And the rest part will be exponential I alpha minus beta plus exponential I minus alpha plus beta and plus 1. This equals 0. So we must have exponential I alpha minus beta plus exponential I minus alpha plus beta equals minus 1. That's the relation here. Now let's try to find Z minus W. So Z minus W, let's do the square of the modulus, which is Z minus W times Z bar minus W bar, the conjugate. And this equivalent to Z times Z conjugate minus Z times W conjugate plus Z conjugate times W and plus W times W conjugate. Right, because Z has modulus 1 and W has modulus 2. So that means for the first term, last term, we know this is 1, this is 4. That means this equals 5 minus Z W conjugate plus Z conjugate W. Now let's write this terms in the parentheses. 5 minus Z times W conjugate equals twice exponential I alpha minus beta. And Z conjugate W, that is twice exponential I minus alpha plus beta. From the above computation, we see that this is minus 1. That means this parenthesis equals minus 2. In other words, the total value here is 7. And then we can take square root, we get root 7. So Z minus W, the modulus is simply root 7. That's the answer here. Question 12. Let S be the collection of all possible complex numbers Z such that Z conjugate 1 over Z form a right triangle on the complex plane. So what can we say about this set of Z? So we try to use this right triangle and find some requirement for Z. Okay, let's assume Z be expressed as A plus BI. And accordingly, we have Z conjugate equals A minus BI. And for 1 over Z, it equals Z conjugate over Z times Z conjugate. And that corresponds to Z conjugate over the modulus of Z squared, right? So it's basically A squared plus b squared in the denominator and a minus bi in the numerator. So those three complex numbers make a right triangle. Let's see what that means. So let's draw some picture to illustrate the idea. For simplicity, let me just draw z in the first quadrant. But actually, z can be on any quadrant. Okay, suppose this is z. The coordinate z conjugate is symmetrical with respect to z about x axis. Z conjugate. So in order to form right triangle, and 1 over z is parallel to z conjugate. So that means on the line of z conjugate. So in order to form right triangle, this is the one. This is a triangle. And here is the 1 over z. So from here, we can use this perpendicular relation to find the equation on z. So this vector actually corresponds to z minus 1 over z, which is a plus bi minus a minus bi over a squared plus b squared. And let's just simplify it. It becomes a times a squared plus b squared minus 1 over a squared plus b squared. That's the real part. And for the imaginary part, it is b times a squared plus b squared plus 1 over a squared plus b squared. This is I. Okay, that's and this complex number is conjugate is perpendicular to a z conjugate, right? And now we know z conjugate is a minus bi. Okay, a minus bi. So let me mark the few points. Let me call this to be a, this to be b, and this to be h. We can use perpendicular relation using the slope of two line connecting 2 points. So slope of slope of AH is basically the quotient of the imaginary part and the real part. So we can just ignore denominator. So it becomes b a squared plus b squared plus 1 over a squared plus b squared minus 1. That's the slope. And also we have a slope of HB. Slope of HB is minus b over a. We know the product of these two slopes equals minus 1. Minus 1 times minus b over a. This equals minus 1. Now we can simplify. That is b squared times a squared plus b squared plus 1 equals a squared times a squared plus b squared minus 1. Right, so we can cancel this a squared times b squared, and finally we have a fourth. Okay, b fourth plus b squared equals a fourth minus a squared. And so we have a fourth minus b fourth equals a squared plus b squared. Now the left-hand side is difference of squares. It can be written as a squared plus b squared times a squared minus b squared. So we can cancel a squared plus b squared. It cannot be 0. Otherwise, we cannot have 1 over z, right? A squared plus b squared cannot be 0. So finally, we have the requirement a squared minus squared b squared equals 1. So this is a standard equation for hyperbola. Question 13. Find the sum of all complex numbers z with modulus 1, and this equation has at least one real solution. So because z has modulus 1, we can assume z equals a plus bi and a squared plus b squared equals 1. And now let's plug in into this quadratic equation. So we have a plus bi times x squared twice z conjugate. So a minus bi and plus 2 equals 0. Now let's suppose this x is real. Okay, say for some real number x. So here we can separate the real part and the imaginary part. We should have a x squared plus 2ax plus 2. That's the real part because x here is real. And then plus imaginary part. I times bx squared minus 2bx equals 0. Now we should have both parts equals 0. And bx squared, okay, let me factor b, x squared minus 2x equals 0. Let's call the first equation, the second equation here. Now from second equation, it's quite easy to see the roots. However, we should still pay attention to b. Probably b could be 0. So let's discuss the cases, okay? First case, we should discuss if b could be 0. If b equals 0. If b equals 0, because a squared plus b squared equals 1, we must have a squared equals 1. This helps to determine z, right? Well, there are just two cases. Let's discuss two cases. In the first case, we have a equals 1. If a equals 1, let's look at the first equation. We have x squared plus 2x plus 2 equals 0. However, it's easy to check. There's no real solution. The discriminant is negative, so no real solution. So we cannot have a equals 1. And second case, we must have a equals minus 1. In this case, we have minus x squared minus 2x plus 2 equals 0. This time we can solve x. X can be solved to be a minus 1 plus or minus root 3. So this case works. That means if a equals minus 1, b equals 0, everything is good. So z, accordingly, z equals minus 1 works. Right, that's the first case. Now let's go to the second case. The second case is b not equal to 0. If b is not 0 from second equation, we are able to solve x. And there are basically two cases, x equals 0 or x equals 2. So we have x squared minus 2x equal to 0. Now there are two cases. The first case, if x equals 0, let's check the first equation. It goes to that. First equation, it has contradiction because first equation says 2 equals 0. So that's impossible. So x cannot be 0. And second, let's consider x equals 2. That's the real solution. And plugging into the first equation, get a 4a plus 4a plus 2 equals 0. And then we got a equals minus 1 over 4. And now we know a squared plus b squared equals 1. That means b equals plus or minus root 15 over 4. Okay, for such z works. So z, if I call this z1, so I have z2 equals minus 1 over 4 plus 15, root 15 for I, and z3 minus 1 over 4 plus, sorry, minus root 15 for I. So the question here asks for the sum of z, okay? Find the sum of all z. So the sum of all z is z1 plus z2 plus z2 is a real number and it's minus 3 over 2. So the answer to this question is minus 3 over 2. Question 14. Z and W are two complex numbers satisfying Z has modulus 2 and W has modulus 3. And 3Z minus 2W equals 1 plus I. We need to find the imaginary part of Z times W. So here, let's try to study this 3z and the 2w. This coefficient matters. It's related to their modulus. 3z minus 2w equals 1 plus I. So we pay attention to this 3 and this 2 because that's closely related to the modulus here. Let's try to plug in. Okay, z modulus equals 2. We can create 2 in the following way. Z times z conjugate, this is going to be 4. I will divide by 2, that equals 2. And also, w modulus equals 3. We can create 3 from w times w conjugate and divide by 3, which is 3 here. And now we replace here. We got w times w conjugate over 3 times z minus z times z conjugate over 2 times w equals 1 plus I. Okay, on the left-hand side, we can factor the common term z times w. We have w conjugate over 3 minus z conjugate over 2 equals 1 plus I here. All right, in this way, we can multiply 6 on both sides to get z times w, 2 w conjugate minus 3 z conjugate equals 6, 1 plus I. All right, here, if we look at, we are interested in z times w, but there's another part in the parentheses. This is closely related to the equation given at the beginning because we have 3z minus 2w equals 1 plus I. We can take conjugate and produce 3z conjugate minus 2w conjugate equals 1 minus I, the conjugate of 1 plus I. And now let's see what's the difference. We just add another negative sign. Implies 2w conjugate minus 3z conjugate equals negative 1 plus I. All right, in this way, we are able to solve z times w. Z times w equals 6, 1 plus I over minus 1 plus I. And we simplify, this is going to be equals minus 6I. Okay, that means the imaginary part of z times w, which is minus 6. And therefore, our answer here is minus 6. Question 15. For how many positive integers between 1 and 100, the following curve has at least one intersection with the circle, unit circle. So in other words, for how many complex number with modulus 1 satisfying this equation? So let's just assume z is an intersection, so z can be expressed as exponential I theta. So according this is cosine theta plus I sine theta. And we have theta between 0 and 2 pi. And then when plugging, there exists certain integer n, make this happen. So z n's power plus z conjugate equals 1. That implies z n's power equals 1 minus z conjugate. That's plugging by De Moivre's theorem. We have z n's power is cosine n theta plus I sine n theta, right? That's the left-hand side. On the right-hand side is 1 minus the conjugate of z. It's basically cosine theta minus I sine theta. It equals 1 minus cosine theta, the real part, plus I sine theta. So let's compare the real part and the imaginary part on both sides. So we can apply double angle formula for cosine theta. This is going to be twice sine half theta square. And for sine, that's I times twice sine half theta cosine half theta. We can factor twice sine half theta. This is sine half theta plus I cosine half theta. Right. Now we have theta between 0 and 2 pi. So half theta is between 0 and pi. So sine must be positive. This should be positive. Okay, not negative. Right. So if we compare these two parts, the left-hand side part and the right-hand side part, we have the following conclusion. Okay, in order to compare, let's also write this parenthesis part into a standard form. Okay, let me use one more step. 2 sine theta half. This is a cosine 1/2 pi minus theta over 2. The real part we like to use cosine. The imaginary part, let's use sine. Now we'll compare. So on the left hand side is the modulus is 1. And the angle is n theta. So we should have the following equations. First, the modulus equals 1. And second, the angle, okay, this pointing to the same direction. So n theta minus pi over 2 minus theta over 2. This should be a multiple of 2 pi, let's say 2k pi. So k is integer. That's the requirement to make the equation hold here. Now from first equation, we have a sine half theta equals 1. Sine half theta equals 1/2. So that means we have two angles. So first case, half theta equals pi over 6, because sine pi over 6 is 1/2. And then we have theta equals pi over 3. And the second case, half theta equals 5 pi over 6. And the theta equals 5 pi over 3. So there are two possibilities. Now, for each possibility, let's plug into the second equation and discuss the value of n. Okay, if you plug into the second equation, for the first case, we would have, okay, let's just cancel pi, because we have pi everywhere. So this is gonna be n times 1/3, and minus 1/2, and plus 1 over 6 equals 2k. Now, this implies n equals 6k plus 1. So n has remainder 1 when divided by 6. That's the requirement here. And now we consider n between 1 and 100. So here k can basically from 0, 1, 2, up to 16, right? There are 17 values here. Okay, we should also discuss the second case. Theta equals 5 pi over 3. In this case, we also plug in, we have n theta, so it's 5n over 3 minus 1/2 plus 5 over 6 equals 2k. Again, we can solve n. Okay, this time we have 5n. We can solve 5n equals 6k minus 1. All right, we see that this is the remainder is 5 when divided by 6. Because 5 and 6 are coprime, we see that n has remainder 1 minus 6. So again, the requirement is the same. These two requirements are the same, because remainder divided by 6 is 1. So still, we have the same values of n. Same n as the first case. So totally, we have 17 solutions. And therefore, the answer to this question is 17. Question 16. We're given a polynomial function f z with 1 plus I is a root, minus m plus square root n is also a root. Now m and n are two positive integers. What is m plus n? So first, there's unknown factor in this function, that is a. We can solve a using given root here. So f of 1 plus I, it equals 0. We can plug in this 1 plus I, fourth power minus 3, 1 plus I square plus 6, 1 plus I plus 8. And we can simplify this into 2 plus A. From here, we can solve A equals minus 2. And now we see that coefficients of f are all real numbers and integers. Actually, we can find some factors. Coefficient of f are all real. That means 1 plus I is a root, implies its conjugate is also root. Because we can take conjugate over the whole function, the function does not change, but root changes to its conjugate. So 1 minus I is also root. And then z minus 1 plus I, z minus 1 minus I are two factors. Two factors. And so we can find the quadratic factor. So is the product, which is z squared minus 2z plus 2. So we can actually factor fz by this factor and another quadratic factor. So we can use long division. Implies f of z equals z squared minus 2z plus 2 times another factor. You can just divide and find the quotient. It is z squared plus 2z minus 1. Okay, now let's pay attention to the second part. This part corresponds to the roots minus m plus n. So we can actually solve z here. This quadratic equation has root z equals minus 2 plus or minus the discriminant, which is 8 over 2. That is minus 1 plus or minus root 2. So there are two roots. Okay, in this question, it says minus m plus n. Actually, there's also minus m minus root n. So we see m equals 1 and n equals 2. That just means m plus n equals 3. So the answer here is 3. Here, we can also use Vieta formula. Let me quickly mention the method 2 using Vieta formula. Because we have the real coefficient, and the integer coefficient. That means the following. On one hand, because real coefficient 1 plus I is a root, means 1 minus I also root. Because you have integer coefficient, we have minus m plus root n is a root. That means minus m minus root n also root. So those two are roots. And then Vieta formula says that the sum of root here, we see it is equals 2 minus 2m. And here the coefficient for z cubed equals 0. So by Vieta formula, this equals 0. We have m equals 1. Also, we can find their product. Their product equals 2 times m squared minus n. By Vieta formula, that is a, okay? That is a, and a equals minus 2. From here, because we already solved m, so we can solve n equals 2. Also, we find m plus n equals 3. Okay, either method works. Answer is 3. Question 17. Z is complex number with argument equals pi over 3. And z, the modulus of z, z minus 1, z minus 2 form a geometric sequence. What is the modulus of z? Because our argument of z equals pi over 3, We can basically assume z equals t plus root 3t I, because that determines the direction. Pi over 3. The ratio for y coordinate to x coordinate is root 3. So we assume that. And then we try to use algebra to solve the relation using the geometric sequence. So z, okay, let's express the z conjugate, z modulus equals 2t, and z minus 1 modulus equals t minus 1 square plus 3t square with square root here by definition. Okay, z minus 2, the modulus equals t minus 2 square plus 3t square with square root here. So these three numbers for a geometric sequence. That means z over z minus 1 equals z minus 1 over, okay, I'm using this common ratio. So I will have z minus 1 over z, that's the ratio, okay? Z minus 2 over z minus 1, okay? This is common ratio. And that implies z minus 1 square equals z modulus times z minus 2 modulus. So this is the equation, and we can plug in, and that will be equation on t, then we can solve t. So when we plug in, we have z minus 1 square, that is t minus 1 square plus 3t square equals 2t times t minus 2 square plus 3t square. Okay, on the right hand side, we can open the squares here. It's 4t square minus 4t plus 4. And the left hand side is 4t square minus 2t plus 1. Right, next we can square both sides to remove the square roots. So it's 4t square times 4t square minus 4t plus 4. And let's simplify the terms. On the left hand side, we have 16t fourths plus 4t square plus 1, the square terms. And the other terms, 16t cubed plus 8t square minus 4t, the cross multiplication terms. On the right, there's 16t fourths minus 16t cubed plus 16t square. Now we can cancel several terms. So first, the t fourth term cancels. And the next t cubed term also cancels. We only have t square term and t term. So that's quadratic equation. Let's simplify it. We simplify this. We have 4t square on the right. And for the t terms, let's move to the right. We have 4t here and minus 1. So that's the equation on t. And now we can solve t equals by quadratic formula, okay, plus or minus root discriminant 32 and over 2. And this simplifies to, okay, over 8. Okay, this simplifies to minus 1 plus or minus root 2 over 2. That's t. Because here t must be positive because the argument is pi over 3. T must be positive. And therefore, we just take t to be minus 1 plus root 2 over 2. In this question, we look for the modulus of z that corresponds to 2t. So it's root minus 1 plus root 2. Okay, so our question to this problem is root 2 minus 1. Question 18. we have a sequence of complex numbers Zn. The first term has modulus 1. And for future 2 consecutive terms, they satisfy these equations. And we try to sum up these finite terms. The modulus is always larger or equal to C. So we try to find the C square. Okay, so let's see this expression. We claim that it does not depend on the direction of the first Z, because if you look at this summation, the modulus, we can factor the first term, Z1, and then becomes 1 plus D2 over Z1, D3 over D2, up to Zm over Z1. Okay, D2, D3 also over Z1. Okay, this is largely equal to C. But we can basically cancel this first term. So it's 1 plus D2 over Z1, 3 over Z1, Zm over Z1. So in this way, we can basically assume the first term is just 1. Let's just take Z1 equals 1. And it does not change the solution in this problem, right? And let's see what's this quotient. First, we notice that Zm over Z1 is a product of this quotient of the consecutive terms. This is Z2 over Z1, Z3 over Z2, and the Zm over Zm minus 1, right? So we pay attention to these quotients of 2 consecutive terms, and that's described in this equation here. So we can divide Zm square in this equation. That means we have 4 Zm plus 1 over Zm square plus twice Zm plus 1 over Zn plus 1 equals 0. And we can solve the quadratic equation to get the information of this quotient. To solve this problem, we get Zm plus 1 okay, we got Zn plus 1 over Zn equals, there are 2 values. It's basically minus 1 plus or minus root 3i over 4. Well, here we can factor 1/2 to get minus 1 plus root 3i over 2, or minus 1/2 minus 1 plus minus root 3i over 2. Now, we can denote this as 1/2 of omega or 1/2 of omega squared. Here, omega is a special complex number. If we draw this complex plane, that corresponds to the direction 2 pi over 3. This is a W, and the angle here is 120 degrees. Okay, and also here is W square. So it's, the angle is 240 degrees, right? So that means the ratio between this consecutive term is 1/2 of omega or 1/2 omega square, okay? And here we already assumed that the first term is just 1. Right, so we can basically calculate the term after 1. We try to see what would be the smallest number here. So notice that Z2 over Z1, Z3 over, okay, let me first estimate that Dm plus 1 over Dn. This is, we know this equals 1/2. And so if we look at D2 over D1, D3 over D1, all these terms, we would see this modulus is smaller equal to 1. It cannot be larger than 1. So we compare these two parts, 1 and the later terms. And this is the last equal to d2 over d1 plus d3 over d1 dm over d1. Because we can apply the modulus to this term, and this will be equal to 1 over 2 and plus 1 over 2 square, all the way 1 over 2 and minus 1. And this is, of course, less than 1. So we have some picture of this problem. We try to minimize the later term. Okay. Let's see what's our goal. Goal is to minimize this modulus. Okay, let me just come back to the original notation. So Z1 and Z2, Zm, right? Here we already have Z1 equals 1. Okay, so to minimize this, we try to maximize. We need to maximize the later terms in the opposite direction. In opposite direction, so they cancel the real part and minimize the whole conjugate, the whole modulus. Okay, so how do we do that? We can try to guess the answer at this moment, and later I will justify the conclusion. I can take this way. I can take a Z2 is basically 1/2 omega, and D3 is 1 over 2 square omega square, because every time the modulus divided by 2. The fourth, it is 1 over 2 fourths omega. The fifth is 1 over 2. Okay, here's cube. 2 cube, 1 over 2 fourths omega square, like that, okay? Like this. So the intuition in this picture is that I'm going to take 1/2 in this direction, and maybe this 1/4 this direction, and then I flip back to this 1/8 of this direction. So we put all the later terms in these two directions. That means we try to maximize this direction, the opposite direction, and it cancels Z1 as much as possible. So in this way, we cancel Z1 as much as possible, and then we make the whole summation with the smallest modulus. Here I'm telling you the intuition, okay, intuition. And let's see, let's compute, okay. In this way, we will have computation. You can use geometric sequence formula, and you will see Z2 plus Z3. We can just take infinity many terms as much as possible. In this way, we will have the summation equals 2 over 3 omega plus 1 over 3 omega square. And then we have this equals minus 3 plus root 3i over 6. Okay. And in this way, 1 plus this term is basically 3 plus root 3i over 6. And we take the modulus, this equals root 3 over 3. So our answer here will be root 3 over 3 based on our intuition, And so C should be root 3 over 3, and then we square it, we get 1/3. Okay, so answer is 1/3. And next part, let me give you some justification why this is always true more rigorously. Okay, let's do justification. So we justified, and to prove this is always true. Okay, so first we notice that the consecutive two terms add up to have constant, to have a modulus that's in a pattern. So this is gonna be Zn 1 plus Zn plus 1 over Zn. And we know Zn has some modulus 1 over 2 to n minus 1's power. is 1 plus, but the ratio, this ratio has two possibilities, -1 plus or minus √3i over 4, but it does not change the modulus. So this will be equal to √3 over 2 to the nth power. So this is constant. And now we can discuss the m, because here we have if m equals 2k, if m equals 2k, we consider the sum of even number terms, the 2m. Because we know the modulus decrease exponentially, and that means the first two terms will give us the largest modulus. We try to split these two parts, the first two terms and the later terms. The first two terms dominate the modulus. So we have this is larger equal to z1 plus z2 minus the later terms. Right. So in this way, we discussed m equals 2k because we can group two terms together and use the above property. And this is larger equal to minus 3, the 4, the 5, the 6, the 2m minus 1, the 2m. Okay. And now let's see what's the expression here. I will just apply the formula. This equals √3 over 2 to the first power, right? And minus √3 over 2 to the third power. And √3 over 2 to fifths. And up to 3 to 2 to the 2m minus 1. So actually, I can try to subtract a little bit more. Suppose I like this sequence to be infinite many terms. So I can keep doing this. And so this changes to larger equal 2. That's still true. In this way, I will find this √3 over 2 minus √3 over, okay, this is going to be √3 over 6. So this is exactly √3 over 3. So if m equals even number, this modulus is larger equal to √3 over 3. That's true. We also need to discuss m equals odd. Let's discuss m equals odd. If m equals 1, that's very easy, right? If m equals 1, it is just 1, of course, larger than √3 over 3. That's very simple. Now, if m equals 2k plus 1, and k is an integer, a positive integer, we can discuss similar condition. But here, something, okay, let me do this. Some additional term is the z 2k plus 1. This can be split into d1 plus d2 minus the future terms. The 2k minus 1, the 2k, but we have additional term here, the 2k plus 1. We try to use the previous idea. The previous idea, we see the difference. Okay, I should modify this 2k minus 1, 2k, 2k here. 2k minus 1. Okay, in the previous part, the idea is we can add this additional term and do the computation. Here, let's compare these two computation. The new term is here. The new term is this z 2k plus 1. We try to compare this z 2k plus 1, the modulus, and this added term here. And if that can be bounded, we're good enough. Note that z 2k plus 1 has the modulus 1 over 2 to the 2k, right? That's what we know already. And now let's compare the other parts. The additional part here will be root 3 over 2k plus 1, root 3 over 2k plus 3, all the way into infinity. Now let's do the summation here. By geometric sequence, we do summation here, we got root 3 over 3 times 2 to the 2k minus 1. And it turns out that this term is larger than 1 over 2 to the 2k. So in other words, in the second case, this additional term is even smaller, okay? We subtract smaller number. So again, we will have the inequality holds. So this is larger equal to z1 plus z2 minus z3, z4. Okay, and this additional term, I just replaced by larger size. So, and this equals root 3 over 3. So this is a justification that our modulus is always larger equal to root 3 over 3. So C is indeed root 3 over 3. And of course, C squared becomes 1/3. So the answer here is 1/3. Question 19. For how many positive integer n between 1 and 100 inclusive, the polynomial p is divisible by polynomial q? All right, here, in order to have polynomial p divisible by polynomial q, that means all roots of q are also roots of p. That's what it means. So let's investigate their roots. Okay, if you look at q, we see that qz times 1 minus z is basically 1 minus z to the 12th power. Okay, so that means q z has the following root. That is omega k exponential I to pi k divided by 12. And here k is start from 1 to up to 11. Okay, for all this one, because omega 12 or z, the value 1 is already a solution from 1 minus z. So for the other 11 roots are the roots for q. So we should consider p. So p is z. Let's sum up this polynomial, okay. And if z to the nth power equals 1, and this is simply 12, and it can never be 0, okay? Now, if z to the nth power is not equal to 1, the summation is 1 minus z to the 12th n over 1 minus z to the nth power. Let's check. So we must have zn not equal to 1. Not equal to 1. If this equals 1, p z cannot be 0. So let's check if omega k is a root. So p, if zn is not equal to 1, let's check p omega k is going to be 1 minus omega k 12n over 1 minus omega k n's power. And we see that omega k is basically omega 1 to the k's power. Omega 1 means exponential I pi over 6 That's omega 1. So we see that omega 1, okay, this is equal to 1 minus omega 1, 12 times nk, 1 minus omega kn. So omega 1, when we add 12 power, it's always 1. It's always 1 because that's the root, right? And so the above equation is 1 minus 1, 1 minus omega k, and this equals 0. It is a root. It is a root, and the denominator is not 0. So we only require Zn not equal to 1. We should find all n, so Zn's power is not equal to 1. And let's see what's the requirement here. So the requirement here is omega k to the 12th power, to the nth power is never equal to 1. Here k, so 1, 2, up to 11. Okay? And it is equivalent to the fact that GCD k, GCD 12 and n equals 1. Equal to 1. Okay, let's discuss. If GCD 12 n equals d, and d is larger than 1, so we can take k equals 12 divided by d. So omega k n, this is equivalent to omega 1 k's power. Okay. It equals to omega 1 12 with additional power n over d, and n over d is an integer. So this equals 1. So that's not required. That's not allowed. So we cannot have GCD larger than 1. So we must have GCD equals 1. And here we have omega k, and this is equals omega 1 kn. And the n does not have a common factor larger than 1 and 12, so this can never be 1, and that's easy to check. So that's our requirement. Let's see how many n there between 1 and 100. So between 1 and 100, let's define the two sets, set A and set B. Set A is all numbers that's divisible by 2. Set B is all numbers that are divisible by 3. So for A, we have 100 divided by 2. There are 15 numbers. For B, it is 100 divided by 3. There are 33 numbers. And now, okay, we also have intersection. That is 100 divided by 6, which have 16 numbers. So we can find the union, A union B, which is 50 plus 33 minus 16, which is 67. So those are numbers with common denominator larger than 1, with 12. Okay, so the answer will be other numbers, 100 minus 67, which is 33. So our answer is 33 here. Question 20. How many pair of complex numbers U, W, satisfying the modulus equals 1 and the following equation holds? Now, because they have modulus 1, we can express U as exponential I alpha and W as exponential I beta. And let's plug in this into the equation. 1 over U is basically exponential minus I alpha. And the U over W is exponential I alpha minus beta. And the W is exponential I beta equals 1. So let's use Euler's formula to express this term. The first term is cosine alpha. Cosine minus alpha is also cosine alpha. And plus I sine is minus alpha, which is minus I sine alpha. That's the first term. And the second term is cosine alpha minus beta plus I sine alpha minus beta. And the third term is cosine beta plus I sine beta. And this equals 1. Now let's split the real part and the imaginary part. So we have a cosine alpha plus cosine alpha minus beta plus cosine beta. This equals the real part, which is 1. And for the imaginary part, which is sine, negative sine alpha plus sine alpha minus beta, and then plus sine beta. This equals 0, the imaginary part. Well, we'd like to derive some information from these two equations. So we can do the following. Let me separate this into cosine alpha plus cosine beta equals 1 minus cosine alpha minus beta. The second one, minus sine alpha plus sine beta equals minus sine alpha minus beta. Let me call this equation 1, equation 2. Now we can square both terms and then sum them up. We solve something. So 1 square plus 2 square. On the left hand side, I have two pairs, a square of sine square plus cosine square, and the multiplication terms. So cosine alpha square, cosine beta square, and plus twice cosine alpha cosine beta, and sine alpha square, sine beta square minus twice sine alpha sine beta. That's the left hand side. Well, basically we have 2 here. This is 1. This is also 1. This one is 1. On the right hand side, we also have 1 minus, okay, twice cosine alpha minus beta plus cosine alpha minus beta square and sine square alpha minus beta. So we have one pair. This pair, this is a 1. And this is also 1. So we can cancel those ones, and also we can divide by 2. On the left hand side, we have cosine alpha, cosine beta, minus sine alpha, sine beta. On the right hand side is minus cosine alpha minus beta. This equals minus cosine alpha, cosine beta, minus sine alpha, sine beta. Now the sine part can be cancelled, and the cosine part are opposite to each other. So we have cosine alpha times cosine beta equals 0. So either cosine alpha equals 0 or cosine beta equals 0. But that corresponds to the angle for these two complex numbers. Let's see, we have alpha, beta between 0 and 2 pi. Now that means alpha beta will be 1/2 pi or 3/2 pi's. Let me discuss two cases. If cosine alpha equals 0, that means alpha equals pi over 2 or 3 pi over 2. Accordingly, we know the value of u. So u equals I, or u equals minus I. Now, if u equals I, we're plugging into the equation. We can get 1 over I plus I over omega plus, okay, w 1 plus w equals 1. This corresponds to a quadratic equation on w. So we have w squared minus 1 plus I w plus I equals 0. And we can solve this by using quadratic formula. You have a w equals 1 or I. We can solve that. And next one, if u equals minus I, we're going to have 1 over minus I minus I over W plus W equals 1. Now you can solve W squared minus 1 minus I, W minus I. Again, you can solve W equals 1 or minus I. This time it's minus I. Because the sum of root here is 1 minus I. And now next time we can discuss cosine beta equals 0. If cosine beta equals 0, we have angle beta equals pi over 2 or 3 pi over 2. Accordingly, we have W equals I or W equals minus I. Now we discuss accordingly. If W equals I, we have 1 over U plus U over I plus I equals 1. That corresponds to quadratic equation on U squared minus 1 plus I, U plus I equals 0. So you can solve U equals 1 or I. But be careful, when U equals I, this is already repeated, okay, at the beginning. When U equals I, W equals I, this is repeated. So here we have one new additional root. And next time, if W equals minus I, we have 1 over U minus U over I minus I equals 1. This equation has U squared minus 1 minus I times U minus I equals 0. So you can solve U equals 1 or minus I. Again, this minus I also repeated because when U equals minus I, we solve W equals minus I, repeated. And totally we have 6 solutions, 6 distinct solutions. 8 minus 2, 6 solutions. Right? That's the answer to this question. Okay, that's all for the solutions.